So, I want to evaluate f on some CTs, right. This is my basic idea of evaluation. So, the first observation is that it suffices for us to look at some simpler gates. I do not need to think of arbitrary circuits. It suffices for me to think about addition and multiplication. So, if I can support addition and multiplication, right, in a way that the resultant ciphertext also has the same form as the original ciphertext, then I can keep going. So, any circuit can be written just in terms of addition and multiplication gates, right. So, we have seen the notion of universal gates. So, in particular the NAND gate is universal, as we have seen, and I can construct a NAND gate using just additions and multiplications, for example. So, my first simplification is that I will just talk about how to add two ciphertexts. So, I need to show you, like, my ciphertexts are matrices, right, C1 and C2. I need to show you how to add them, and I need to show you how to multiply them. Okay. So, addition is actually amazingly simple. So, it is just literally add, and it is also very easy to see why this works. So, by the way, I should mention that supporting only addition is actually very easy. You could do it even in a lot of other schemes. Like we saw the El-Gamal encryption scheme, you can check that it will also satisfy one direction of homomorphism. Okay. So, here we support both directions, both addition and multiplication. That is what is meant by fully homomorphic. Okay. So, that is what was very challenging to achieve. So, addition is very easy, and like I said, I will very easily prove to you that this works, right. So, my ciphertext is this, right. Okay, I am pointing to C2, so I should write 2 over here, or I will just change the arrow. Okay, so C1 plus C2 is what? So, AR1 plus mu1G plus AR2 plus mu2G, correct. This is what my ciphertext looks like. So, this is obviously AR1 plus R2 plus mu1 plus mu2G. So, you can see I just call this A whatever A R plus mu1 plus mu2G. So, I got back the same ciphertext, right. So, my decryption will work. So, it is again AR plus mu G, where now mu is mu1 plus mu2, exactly the way that I wanted. Okay. So, addition works. So, multiplication of course is the key challenge over here, and we will see that in fact there is a very elegant way of doing it. So, to multiply C1 and C2, a first thing to observe is that C1 and C2 are not square matrices, right. So, they are fat matrices, right, n by m. Okay. So, what would be my dream way of multiplying these two ciphertexts? I would love to just multiply them, right, as matrices. I mean this is the most appealing idea, that whatever circuit I was going to compute on my plain texts, I just compute exactly the same on my ciphertexts, right. My ciphertexts are matrices instead of bits, no matter, but I can add them, I can multiply them. That would be my dream. Now, that dream does not quite pan out, but something very close to it actually does in this case. So, I have to in particular make allowance for the fact that the two are not square. So, what will I do? Okay, so I take C1 which is n by m, and now I need to multiply it with something which is m by m, right, because this is n by m. So, okay, if not m by m, then m by something, right. So, because I need the dimensions to work. So, take a wild guess, how should I take my second ciphertext, and it is n by m, I want it to be m by m, right. M is n log q. Okay, now think like a cryptographer. My C1, what is my C1? It is AR1 plus mu G. A has noise in it, does it not? A has LWE sitting inside it. If I multiply something with noise with something over ZQ, can I ever get back, can decryption ever work? What did I tell you is the main, the simplest goal in scheme design from LWE. Not the simplest goal I should say, but the sort of the guiding rope that I can hold on to, right. At least that has to hold. The noise should never blow up. Whatever else you do, anyway it is going to be hard to make correctness and security work, no matter what you do. But at the very least, like a necessary but far from sufficient condition is to keep the noise from blowing up. So, since my C1 has noise in it, if I pad C2 with zeros or take transpose or something, will that prevent the noise in C1 from blowing up? What will prevent it from blowing up? Yes, I would like C2 to be a low norm matrix, very good, yes. And what is the only way that we have seen in going from a matrix to a low norm matrix, which also magically satisfies the dimension requirement? Excellent, exactly, pretty much. I mean, so GSW came up with this, from air, right. Here we are giving you each piece and saying that, okay, I told you I want to like flatten down these entries, right, because the noise will blow up otherwise, and I gave you exactly one method to do it, right, and we also noted that the dimension will blow up, right, and I also told you that m is n log q, and that is what we are missing. So, very good. G inverse C2, okay. And why should this work? So, first of all, with the addition, let's keep it as an exercise that this decrypts. I want to argue that decryption of C1 plus C2 is trivial because it is merely AR plus mu G. So, I showed you how to decrypt AR plus mu G, and this is exactly that. So, this should certainly work. Now, for multiplication to work would need a little more work. So, let us see. Okay. So, I have T which is my key, C1 G inverse C2. Okay. This is my first step of my decryption. So, after that there is also the G inverse W that we do later, right. So, T times C1 is what? We already figured that out, right. So, it is approximately mu 1 Tg, everyone agrees? We already worked this out, that T times C is mu Tg roughly. So, mu Tg times G inverse C2 is what? So, now let me take mu 1 out. Now, G and G inverse will again cancel, right, because again it is powers of 2 and bit decomposition. So, mu 1 T C2, and now what is what is T times C2? So, again this is going to be what? It will be mu 2 T G, right. So, what did I get? So, I got mu 1 times mu 2, okay, T times G, and now I multiply that G inverse W transpose, right. This was what I was doing in decryption. So, I get mu1 mu2 Tg G inverse W transpose, and this we already saw is mu1 mu2 q over 2. Remember, so we said this is minus s comma 1, W is zeros followed by q over 2, G inverse go away. So, I got mu1 mu2 q over 2, and that is what I wanted, right. Now, note that in the lecture so far I have been extremely hand wavy about the noise blow up. Okay. So, this can of course be bounded properly. I think that anyway in today's class we do not have time. I am not sure if we should spend more time, let us ignore the bounds on the noise for now, alright. So, the intuition holds, and we can of course bound the noise. So, what did we see? We saw an encryption scheme which allows addition and multiplication, right, and we saw that decryption works out for both cases. So, since I have only a few minutes left, a basic thing to talk about is security, right. I mean, correctness, we said that modulo bounding the noise properly, correctness holds. So, what about security? So, what kind of security do I want from this scheme? What does the adversary get to see? The public key and some ciphertext. The ciphertext should correspond to 0 or 1. Now, you may wonder if the fact that this scheme is fully homomorphic means that the security notion should be somehow more sophisticated. Turns out actually no, right. So, homomorphism is something which is a functionality. It does not mean additional power to the adversary. The adversary still does not get any secret key, right. The adversary only gets the public key and some ciphertext. So, it will suffice for me to show that the ciphertext and the public key do not leak anything about the message. So, now what is our public key? Our public key is A, which is in turn a random matrix B and some LWE sample. This is our public key. And what is our ciphertext? It is AR plus mu G, right. So, there is a very simple security proof. Okay. So, in step 1, I replace A by random, and this will hold by LWE, correct. So, this is again like the argument we did yesterday. So, the ciphertext is a function of the public key. So, if I change the public key, I can still generate the ciphertext. So, no problem. So, I replaced A by random, yeah, and now so now my public key is completely random. B was anyway random. Now, small b, which is the LWE sample, also became random. So, my public key is completely random. And now, what is my ciphertext? AR plus mu G. So, this is why we introduced leftover hash lemma. So, by leftover hash lemma, we can say that AR is random, and if AR is random, then AR plus mu G is also random, right. So, once again AR acts like a one time pad. Okay. So, I always find it very cool that this problem was open for such a long time. It was posed in 1978, and it was the first solution came out in 2009, that was by Gentry, and that was a very complicated scheme and not from any very clean assumption either. And then there was a long sequence of works which improved the underlying assumptions and simplified the scheme more and more, right, improved the parameters, and finally we are at a scheme which is so simple that in one class we can essentially show the scheme. So, this is the definition of really good science. Are there any questions? Is the scheme clear to everybody? The reasoning, the correctness, why homomorphism works, and security is very easy. It's just what we did yesterday, but instead of using LWE twice, we use LHL and LWE. And by the way, if you want to use LHL, you don't need the Hermite normal form that we used last time of LWE. So, you can also have a basic PKE, obviously I mean FHE is in particular a PKE, but you can have other variants of PKE as well. So, there are many by now. Any questions? All right, so let us stop here. Thank you.